Bismillah Rahman Rahim. Hello and welcome Professor and dear classmate to my presentation. My name is Rehan Ullah. I belong to Pakistan. My hobbies are hiking, researching and minor repair at home. My hometown is Dirlur and I love rice and Russian tea cake as a food, and my tourism attraction is toward exploring new places. Currently, I am studying PhD at the Department of Biomedical Engineering, Chungyang Christian University. My MPhil in zoology was from Government College University, Pakistan, and my bachelor in zoology was from University of Malakand, Chakdara, Pakistan. My research interests including nanobiotechnology, neuroscience, physiology, and environmental sciences. Today I am going to present about spectroscopy and most definitely about the Fourier transfer infrared or shortly FTIR spectroscopy. FTIR is an analytical technique that used to identify and quantify molecular structures. It is a type of non-destructive analytical technique and it used to measure the absorbed wavelength by various sample material. In domain knowledge, we have different type of spectroscopy. For example, in infrared spectroscopy, it is used to determine the functional group present in molecule of the sample. And mass spectroscopy used to measure the masses of the sample molecule. And nuclear magnetic resonance spectroscopy or NMR used to distinguish between isomers, and ultraviolet or UV spectroscopy used for the bonding patterns present in a molecule of the sample. So we have different type of magnetic spectrum. For example, X-rays, microwaves, radio waves, visible lights, IR, and UV. These are different type of the electromagnetic spectrum. All these are spectrum have different frequencies and wavelength, and most importantly the frequency and wavelength are inversely proportional, and they are combined by equation called C is equal to lambda nu, where lambda is the wavelength and nu is the energy or frequency of the spectrum. And energy are represented by photon. So photon is a packet of energy and it is equal to the h nu, where h is the Planck constant. So the wavelength and energy are inversely related. As we go from gamma rays to radio rays, the wavelength increases, but on the other hand energy decreases. But from radio rays to the gamma rays, the energy increases proportionally. So the energy and wavelength are combined together by inverse relationship. As we see, as the energy increases, the wavelength decreases. But on the other hand, when the wavelength increases, the radiation energy becomes lower and lower. So the infrared region, it is just below the red region in the visible, and its wavelength bandwidth ranging usually between 2.5 and 25 micron. So the most common unit for the wavelength use is wave number. Wave number are per centimeter. So it is the reciprocal of wavelength in centimeter. Wavelengths are proportional to the frequency and energy. So there is a relation that show that the wave number is reciprocal to the frequency or energy of that bandwidth. We have a different type of molecular vibration that covalently bonded molecule vibrate at certain frequency between the equilibrium bond length. So they may be stretch vibration or just like spring or compress vibration. So there is a to and fro moment or vibration between the equilibrium bond length of molecule, and this vibration is mostly continuous vibration. So if we have a non-linear molecule and there are n number of atoms present in the molecule, we can determine the vibrational mode by an empirical formula called 3n minus 6. So if we have 3 number of molecule, so we have in a molecule three number of atom in a molecule. So we have three type of vibrational moment or vibrational motion. They may be symmetrical stretching. They are in 180 angle away from the central atom, or they may be antisymmetrical stretching, one toward the central atom and another away from the central atom, or they may be bending or scissoring, this in one in clockwise direction and other is in anti-clockwise direction. So we have mostly two type of stretching. One is simple stretching and another is complex stretching or complex vibration. And the complex stretching or complex vibration range between 600 and 1400 per centimeter, and this region is called fingerprint region. So whole molecule may be vibrate or bend. So these vibration and bending can be quantized, can be measured. But it is important that two molecules have no the same or the exact IR spectrum or the same vibration. So simple molecules stretch between 1600 and 3500, while the complex vibration or the fingerprint region occur between 600 and 1400 per centimeter. It is a schematic diagrammatic presentation of a simplified spectrophotometer. We have a glowing wire and we have to compare our sample with the reference sample, and it is controlled by a rotating segment of mirror and driven by a motor. And then we have a monochromator to identify certain type of the spectrum, and then we have detector, and detector record the charts. It means that how much energy absorbed by molecule and how much energy passing through the molecule that's under concentration. The application of FTIR spectroscopy is the as I already mentioned in the above slide, is the determination of the functional group present in a molecule. So carbon-carbon single bond is a functional group. Carbon-carbon double bond, carbon-carbon triple bond also are functional group. So the carbon-carbon single bond vibration occur at 1200 per centimeter. So it will absorb the energy of IR, and 1200 per centimeter. The carbon-carbon single bond will absorb energy at 16 and 60 per centimeter, and the carbon-carbon triple bond will absorb energy of 2200 per centimeter. But when there is a conjugation between molecule, the bond absorption energy will be lower. So for let's suppose if we have carbon-carbon single bond but there is no conjugation with other atom, the absorption will occur at 1640 to 1680. But if there is a conjugation, the absorbance of the energy will be lower, and it will be occur at 1620 and 1640 per centimeter. But if there is a lot of the conjugation that occur just like an aromatic hydrocarbon like phenol or benzene, so the absorbance will become lower and lower, and mostly it occur at the range of 1600 per centimeter. Carbon hydrogen stretching bonds with more S character absorb at a higher frequency. Let's suppose we have three type of hybridization: sp3 hybridization, sp2 hybridization, and sp hybridization. As compared to the sp hybridization, there is a less S character in sp3 as compared to the sp. So in sp the S character is more, so it will absorb at high frequency, that is 3300 per centimeter. As compared to the sp3, it is just below the 300, and sp2 is between these two absorption frequencies. It is a simplified IR spectrum of the alkane. So there is a stretching of the carbon hydrogen bond and at 3000 per centimeter or wave number, and there is a carbon and hydrogen bending between 1600 and 1400. So this is an example of N-hexane. For N-alkane IR spectrum, there is a stitching between the carbon, double bond carbon, uh, and bonded with hydrogen at 3080, and there is also another stitch for alkane because there is also some single bond present. Let's suppose we have hexene. There is a lot of carbon-carbon single bond and also with a carbon-carbon double bond. So the carbon-carbon double bond stitch occur at 1642, and there is also another carbon hydrogen bending that occur between 1600 and 1400 wave number are per centimeter. Similarly, for the alkyne with a triple bond, there is a stretching of the carbon-carbon triple bond at 3313, and there is also a stitch, but the difference that here is the presence of hydrogen, but for purely triple bond there is a stitching between 2100 and 19 wave number. This is an example of 1-octane. Similarly, there is no stitch for the carbon-carbon carbon triple bond and hydrogen, but for alkane, because there is also a lot of single bond present, so there will be the characteristic peak between 300 to 2900 per centimeter or wave number. There is also a small stitch, but it is mostly not visible for carbon-carbon triple bond, and this is an example of 4-octane. Okay, OH and NH stretching, both of these occur around 3300 per centimeter of wave number, but their peaks are different. For alcohol, let's suppose we have one round tip. The peak will be the peak step will be round. For secondary amine and primary amine, the peak will be different. So for the secondary amine mean that the NH group or amino group attached to the second carbon. So there will be only one sharp spike. But for the primary amine, there will be broad 2 or 3 sharp spikes. But there will be no peak for the tertiary amine. The tertiary amine are those amine in which the amino group attached to the carbon 4 or carbon attached to other 4 carbon, and one carbon is replaced by the amino group. So there is a OH stretch between 3500 and 3500 per centimeter or wave number, and 2800, and also there is a saturated carbon hydrogen stretching at around 3000, and this is an example of 1-butanol. And there is also another stretch for the carbon oxygen single bond. There is also a stretch occur, but it is mostly non-present in most of alcohol. This is just a case of for the 1-butanol or similar alcohols. For amines IR spectrum, there is stretch between nitrogen and hydrogen, and the spike occur between 3500 and 300 per centimeter, and here is also a saturated stretching between carbon and hydrogen between 300 and 2800 per centimeter or wave number. So it is an example of propylamine. The carbonyl stretching. For carbonyl stretching, the carbon oxygen double bond of simple ketones, aldehydes, and carboxylic acid and others mostly around occur between 1710 wavelength, and it is usually the strongest part of the IR region, And carboxylic acid have also OH group just like the alcohol group, but the peak in alcohol group and for the carboxylic group is different due to the carbon partial partial charge. So aldehyde have 2CH signals around 2700 and 2800 per centimeter R wave number. So this is an example of saturated, and also we have a stretch of the carbon oxygen doubly bonded. There is a double bond between the carbon and the oxygen, and the peak occur mostly between 1700 17 and 1800, and this is an example of 2-heptanone. Per aldehyde spectrum, there is also a saturated stretching occur between carbon and hydrogen single bond, and there is also a stretch between the carbonyl group of aldehyde, and this occur between 27 and 20 and 28 and 20 number or per centimeter. And there is also a stretch of the carbon oxygen double bond, and it occur mostly between 17 and 20, and it just moving when the carbon and the hydrogen and the carbon oxygen bonds strong, because when there is hydrogen or hydroxyl group attached to the bond, the carbon this stretching moving toward the 1800 then 1600. So the bond frequency increases when there is a saturated point. So it is an example of butyl aldehyde. Similarly, there is a OH stretch of the carboxylic acid. This OH absorbs broadly 25 to 3500 centimeter, and it is a strong bond due to the presence of the hydrogen bonding. So here is a stretch exists between OH group and CH stretch between 3000 wave number, and there is also a stretch between carbon oxygen double bond at the range of 1711. So it is an example of hexanoic acid. Vibration and carbon oxygen double bond absorption. Conjugation of carbon oxygen with similarly to those that occur in the alkyne, alkene and alkyl group. So the conjugation of carbon doubly bonded to oxygen and carbon double bond lower the stretching frequency to 1680 per centimeter. The carbon oxygen double bond group of an amide absorb it in even lower frequency, and it's ranging between 1640 and 1680 per centimeter. And the carbon oxygen double bond of an ester absorb at a higher frequency, and that may be range from 1730 to 1740 per centimeter. And the carbonyl group in a small ring, let's suppose we have a phenol or benzene are less than 5 carbon, so it will absorb an even high frequency. If we increase the number of the carbon, the absorption frequency will decrease to lower and lower state. So there is also a stretching occur between the carbon and nitrogen bonding, and the carbon nitrogen bond mostly absorb at frequency of 1200 centimeter per centimeter, and the carbon nitrogen double bond absorbed around 1660 centimeter, and it is a stronger region for the carbon nitrogen, and for the carbon in carbon double bond absorption in the same region, it will occur at the same manner. So the carbon and nitrogen triple bond absorbed strongly just about 2200 per centimeter, while the alkyne carbon triple bond signal is much weaker and is just below 2200 per centimeter. So it is the summary of the IR absorption spectroscopy. The nitrogen hydrogen single bond, oxygen and hydrogen single bond, carbon and hydrogen single bond mostly occur between 3500 and 2500 wave number. Similarly, for the carbon triple bond, for carbon nitrogen triple bond, it occurs between 2500 and 2000 per centimeter, and for the carbon double bond, carbon oxygen double bond and carbon nitrogen double bond, it occurs between 1800 and 1600 per centimeter. And The fingerprint region is between the 600 and 1400, and it occurs mostly for the carbon-carbon single bond, carbon-oxygen single bond, and carbon-nitrogen single bond. So it is a novel technique. It uses an interferometer, and it has better sensitivity. Interferometer are more much sensitive than other type of the spectroscopy, and it use less energy from source, and their scan is very quick, and it complete mostly in 1 or 2 seconds. And the another advantage is that can combine different skin and can take the average of different skin and can show the results. So if we have one FTIR, we have different type of peaks simultaneously measured. So it also use a beam of laser that keep the instrument accurately calibrated. So these are the novelty of the FTIR spectroscopy. But there is also some limitation. Before going to limitation, we have the advantage of FTIR spectroscopy, because it measures the functional group present in a molecule. If there is no signal for a molecule, it means there is no functional group present in a molecule. So it is a 100% accurate technique that can tell about the functional group present in a molecule. But corresponding with known sample, they identified other unknown sample. When we compare the FTIR, the known sample, to the unknown sample, so we can accurately determine the chemical composition of known sample. But there is some limitation that FTIR cannot only determine a structure. We have to extend this technique with certain other type of technique to determine the exact molecular structure of a molecule. There is also some ambiguity and also can produce noise, and these noise have a different type of wave number, so it will be difficult to interpret when these ambiguity or these noising signal can occur in the FTIR and FTIR spectroscopy results. So after this, if you have watched my presentation carefully, you will be able to answer this question. So I am dropping this question and you can answer. So the question is, what is the primary advantage of using Fourier transform infrared spectroscopy, or shortly FTIR, over dispersive infrared spectroscopy? Thank you so much. Thank you for watching. See you next time.